picking up where we left off last time, there's another way that we can represent sets, and that is by what we call Venn diagrams. Now, Venn diagrams are just a way to represent things by a picture, and in which case, sets are denoted by circles, and the big universal set, as you see here, is denoted by a big rectangle. Now, when we draw pictures for Venn diagrams, we want arbitrary Venn diagrams, and what that means is there's no hidden assumption. So you should not draw a picture where there's some assumptions that maybe your problem doesn't have. The way that you can draw an arbitrary Venn diagram of one set is just, there's the universal set, and inside here is the set A. Right? Now, understand that the universal set contains everything, all of that. So the universal set, remember, contains all elements, hence it contains all sets. This thing on the outside is just a piece of the universal set. Here is an arbitrary Venn diagram involving just one set. Here is an arbitrary Venn diagram of two sets, A and B. Notice that there's a possibility that they have elements in common. They don't have to have elements in common, but there should be a possibility, and that's why you draw this arbitrary Venn diagram with some overlap. If you draw a Venn diagram of two sets and it looks like this, that's not an arbitrary Venn diagram because it's got a hidden assumption. What's the hidden assumption? That those two sets don't overlap. Okay, so here's an arbitrary Venn diagram of two sets. No hidden assumptions. Here is an arbitrary Venn diagram of three sets where all possible overlaps are pictured. You can also have an arbitrary Venn diagram of 4 or 5 sets, but life gets really complicated. Remember, just because I have a piece here of overlap doesn't mean there has to be any elements in there, but there should at least be the possibility. Hence, here are the arbitrary Venn diagrams for 1, 2, and 3 sets. All right, last time we talked about the binary operations. And so now I'm going to represent the binary operations by these Venn diagrams. So if I want to represent A intersect B, recall from last time, that's all the elements that are in both A and B. What would my arbitrary Venn diagram look like? And the answer is, I'd have to color in this piece right here, right? Those are the elements that are in the intersection. If I wanted to draw an arbitrary Venn diagram of A union B, what would I do? Well, A union B means it's either in A or in B. My arbitrary Venn diagram would look like that, right? If I wanted to draw an arbitrary Venn diagram of A not B, remember set subtraction, what would I do? I'd have to start out with A and I'd throw out anything in B. So I'd have to throw out this piece and I would end up with what I just got colored in right there, right? That's A not B. By the same token, if I wanted B not A, I would start with everything in B, but then I'd throw out stuff that happened to be in A. And that would leave me with this piece over here. So there's are some pictures of arbitrary Venn diagrams for these binary operations that we talked about before. Now, in addition to binary operations, I have a unary operation, and it's called complement. And it's denoted, depending on what book you pick up, by a little twiddle or a slash, or your book uses a bar above a set. So twiddle A or slash A or A bar all mean the complement of A, depending on which book you happen to pick up. I'll go with the notation that your book uses. So what is A complement? And the answer is A complement is, in set builder notation, the set of X such that what? X is not in A. Remember previous notation? So it's everything that's not in A. And if I want to draw a Venn diagram of that, I'd have, here's my arbitrary Venn diagram of one set. What is not A? And the answer is it's everything on the outside here. Okay, Venn diagrams are very useful in trying to figure out whether or not two set theory expressions are equal. And here I'm going to claim these two set theory expressions are equal, namely the complement of A union B turns out to be the complement of A intersect the complement of B. Now that might look familiar from symbolic logic. Do you remember the negation of A or B turns out to be the negation of A and the negation of B? Well, this is similar. In fact, it's called the same thing, one of De Morgan's laws. So De Morgan's laws apply for set theory. Now I'm going to show you how we can reason that these two sets are the same. First, I'm going to look at this set right here, the complement of A union B. Well, what does that mean? It means I take A union B, that's the inside here, right? And then I take its complement, which means I take everything else but that. So if I look at this, what I end up with is just what's on the outside. Yes? But now I'm going to think about this expression, A complement intersect B complement. Now what is A complement? And the answer is A complement is everything that's not in A. And I'm going to draw that on my Venn diagram by little red marks. So everything that's not in A is all this piece here, right? Everything that's not in A. By the same token, everything that's not in B is this piece right here, and I'm going to denote those with blue marks. And then I look at this expression, and I want everything that's what? both red and blue. So if I look at red and blue, that's all the pieces that have both red and blue marks. And where does that end up being? Exactly this piece out here again. So you can see how we can reason by an arbitrary Venn diagram that those two sets are the same. I'd like to also remind you that there was another one of De Morgan's laws, and there is an analogous law here in set theory that tells us the complement of A intersect B, sure enough, turns out to be the complement of A union the complement of B. But I'll let you think about that yourself and draw yourself a little arbitrary Venn diagram of both to verify that they have the same number of elements. Okay, finally, I want to talk about another set, special kind of set, called the power set of A. And what's the power set of A? I denote it by a script P of A. It is the set of all subsets of A. So the power set turns out to be a set of all subsets. What does it mean to be a subset? Well, A is a subset of B, also written like this. Notice how it opens up to the bigger set, like the alligator eats a bigger number with respect to inequalities. A is a subset of B in case, and now I'm going to define it in terms of a conditional statement. The conditional statement is, if X is in A, then X is in B. Now, think about what it means for that conditional statement to be true. How do I prove a conditional statement is true? By proving it's never false. How do I prove that? I assume the hypothesis, X is in A, and then I have to show the conclusion is necessarily true, namely X is in B. So anytime you're trying to show A is a subset of B, you choose an arbitrary element of A and show it has to be in B. That's what the concept of subset means. And finally, I want to talk about one more piece of notation. If I have an absolute value, that's what it looks like, A, of course, it doesn't make sense to be absolute value because A is not a set. What I mean by that is the cardinality of A. And what's the cardinality of A? The number of distinct elements in A. So I simply look at all the elements in A and I count how many of them are distinct. That is, I don't allow repetition. So the cardinality of the null set, what is it? The answer is 0. There's nothing in the null set. The cardinality of the set 2, 3, 4, well, I count how many distinct elements I have in there, and the answer is 3. By the way, the cardinality of the set 2, 2, 3, 4, since repeating an element twice doesn't make any difference, I still just have 3 distinct elements. So the cardinality of that set is also 3. And I think I will stop there and we'll pick up next time.